Okay, so let's have a look at some applications of Bayesian games now, beyond the conflict example that we've looked at before. And one of the areas that understanding incomplete information games has made a huge impact is in understanding auctions and incentives to bid in auctions. So let's have a look. We'll start with a very simple version of an auction, and then we'll actually look at some more complicated versions of auctions and more realistic versions as we go along. Let's start with a simple version. So we have two bidders. They're bidding for painting. And we'll look at what's known as a first price auction, and we'll think of a sealed bid auction. Okay, so they each, in this case, have a value for the painting. So the type of the players is theta I, and it just specifies how much they're willing to pay for the painting. How much do they value the painting? So let's keep things simple. Let's suppose that they have a value of either 2 or 3, say dollars or thousands or millions, whatever you like. So they either value the painting at 2 or 3, and equal likelihood. So there's a half a probability that they wake up and they think the painting's worth 2, half a probability that they wake up the painting's worth 3, and we'll think of this as IID. So if I wake up and I think the painting's worth 2, the chance that the other person thinks it's worth 2 or 3 is an even coin flip. So what I end up thinking is completely independent of whatever they like, how much they like the painting. So our tastes are completely orthogonal. We wake up, we decide how much we like the painting, and now we have to put a bid in an envelope and send it off to the seller. So first price auction, what does that mean? First price means the highest bidder wins, and they pay their bid. So first highest price is the winner and pays that particular bid. Okay, so let's think of a game now. We've got a Bayesian game. We know what the types are. They're either 2 or 3 with equal probability. The players have to bid in whole integers. And in this case, in terms of specifying payoffs, it's quite simple. What's your payoff? It's how much you value the painting minus what you pay. So if you win the auction, you're going to get theta I minus your bid. If you lose, you get 0, right? So the payoffs are going to depend on what the actions are, which will determine, first of all, whether you end up having the highest bid or not. And then what you get is, if you win, you get your value minus how much you bid. If you lose, you just get 0. Okay. So this is a fully symmetric world. So let's keep our lives simple and look for a symmetric equilibrium, and we'll look for one in pure strategies. So what we need to do is specify, so in a symmetric equilibrium, we have each player we need to specify what they would do if they had a value of 3, what they would do if they had a value of 2, and so that no player would choose to change their bid if they were both bidding that way. So they're both happy maximizing their payoff, expected payoff, given these bids, if this were the situation. Now, let me just say a couple of words about looking for equilibria, searching for equilibria in these kinds of games, symmetric, asymmetric, and so forth. So there's no easy recipe for always finding equilibria. So in worst case scenarios, when you're faced with games, you might have to just actually exhaustively look through what are all the possible combinations of strategies that are possible, and solve and find out which ones are equilibria. It's a little bit of an art in the sense that there are things that we know about the structure of the games that give us hints as to how to proceed. And here we have a fully symmetric setting. In fully symmetric settings, generally there'll exist a symmetric equilibrium, at least one in mixed strategies and sometimes in pure strategies. So that's a useful starting point. And then we can go through and use some logic to try and thin the field down in terms of what we might be looking for. So it's a little bit like looking for solutions to differential equations. There are different rules of thumb. There's structure, which helps you guess how to proceed. But largely, there's no easy and set algorithm that's always going to find equilibria easily for you. Sometimes you're going to have to struggle a little bit and search through. But here we have a nice simple setting. It's a symmetric setting that gives us an idea of how to proceed. So we look for symmetric equilibrium, and basically what we have to do is specify what should the person do when they have a value of 3, how should they bid if they have a value of 2. Okay, so first of all, one thing to note, so they have to bid whole integers. We can try various combinations. So you never want to bid more than your value, because then if you end up winning, you're paying more than you value the object at. You're going to get a negative payoff. You're better off just not bidding at all, or bidding 0. So a second bid that we might consider is what if you bid your actual value? So if I have a value of 3 and I bid 3, well, then my payoff is 0 no matter what. So if I lose, I get a payoff of 0. If I win, I'm paying theta I minus my bid. Right? So if I win, if I'm bidding my value, I'm going to get 0 if these two things are equal. So in that case, my payoff is 0 no matter what. So basically in a first price auction, it's going to be in players' interests to shade their bids. What does that mean? To bid less than their value, in hopes that when they win the object, they're paying less than they value it at, and they're getting some positive payoffs. Okay, so a natural thing to try is that they're going to bid, when their value is 3, they're going to bid something less than 3 in hopes of winning some payoff. And when their value is 2, they're going to bid less than 2. So we can start by looking for an equilibrium of that form. Well, what's an easy one to try? Let's try bidding 1 below your value. So in this case, we'll bid when your value is 3, bid 2. When your value is 2, bid 1. Okay, so let's check. So if we just want to check if this is a symmetric equilibrium. So if the other player is bidding according to this, if theta I is 3, the other player uses this strategy, what's my expected utility? Well, if I bid 3, I'm getting, we already just went through this, I'm always going to get 0. So win or lose, no matter what, I'm going to get a payoff of 0. If I lose, I get 0. If I win, I'm bidding my full value. I get nothing out of it. So that gives me a payoff of 0. If I bid 2, what happens? Well, when I do win, I'm going to get my value of 3. The price I pay is 2. So this is the bid. This is my theta I. So my value is 3 minus 2. What's the probability that I win? Well, the probability, there's a 50-50 chance that the other person is a low type or a high type. If they're bidding according to this function, there's a half a probability that they're going to bid 1 and a half a probability that they bid 2. So if I'm bidding 2, there's a 1/2 probability that I win outright. And there's a half a chance that we tie. And if we tie, we have the seller just flip a coin. They decide randomly who wins. So there's a half a chance that we tie, and then a half a chance that I win the coin flip. So I end up winning with a probability a quarter. So what's my overall value from this? 3/4. Okay. What would happen if I bid 1 instead? Well, if I bid 1 instead, I get a higher value here. So when I do win, I end up with paying less. That's great. I get the painting for less. But the chance that I win is now only when I match. So if I'm bidding 1, the only time I'm going to win is when the other person bids 1 and I win the coin flip. So there's a half a chance that the other person bids 1, a half a chance that I win the coin flip, overall probability of a quarter. So here, 3 minus 1, 2, a quarter, we end up with a value of a half. So here, I'm better off bidding 2 than bidding 1. And if I bid 0, well, I'm never going to win. The other person's always bidding above 0. I get a payoff of 0. So here, my unique best response, if the other person is bidding according to this, unique best response when theta I is equal to 3 is to bid 2. Right? So if the other person is bidding 2 and 1 in this manner, then indeed, when I have a value of 3, I do want to bid 2. So that holds together. Okay. So we also need to check that the bid of 1 when your type is 2 is a best response. We can go through there. Well, what happens if I bid 3, I'm bidding above my value. So I'm going to get, whenever I win, I get a payoff of -1. And now I'm outbidding the other player all the time, so I'm going to win for sure. I'm going to get a payoff of -1. If I bid 2, well, win or lose, it doesn't matter. I get 0 because I'm always bidding my full value. So even when I win, I don't get anything. If I bid 0, I lose for sure. So the only really bid that makes sense in this case is bidding 1. Here I get some positive value when I win. I win with probability a quarter, right? I win when the other type is actually a low type, also bidding 1, and then I win the coin flip. So I end up with a value of a quarter. So here, my unique best response is when theta I is equal to 2 to bid 1. So indeed, we've checked that if the other player is following these strategies, then in fact, I strictly care to follow these strategies. These are my unique best responses. So this is an equilibrium. And it's a symmetric, pure strategy Bayesian equilibrium. It's a strict equilibrium, so it's a strong equilibrium. And so basically Bayesian equilibrium has given us an analysis of this game, which allows us to make predictions. In this case, the bidders will shade their values, how much lower than their value they bid. So here, when you're type 3, you bid 2. When you're type 2, you bid 1. This gives us some idea of how things might work in an auction. We'll take a look at a little more elaborate example of an auction next. That'll give us a little more insight into what's going on, but this illustrates the basic definitions and allows us to see how things proceed.